Okay, let's start. So today, last time we talked about correlations, games, and lower bounding MIP star. Today, and this was, okay, at least the first part of the talk was quite mathematical, but the second part of the talk was very computer sciencey and complexity class and so on, complexity classes and so on. Today, we are going back to the math, to the more the model, modeling quantum mechanics and pure operator algebras and things like that, and finite approximations of algebraic structures. So hopefully we will go through points 2 and 3, and the next lecture will be dedicated to some kind of an overview of the main tools required for the proof of MIP star is equal to RE, like what are the main points in the proof and methods and so on. And after that, we will try to dive into more details. Okay, so I'll start from some reminders. Okay, you see my screen. I think this is good. Good, only that. Okay, so a quick reminder of what we talked about last time. So there were questions in the chat about the choice of OA, OB, IA, and IB. So the point is that the definition of correlation sets clearly depends on the sizes of OA, OB, IA, and IB. So if you fix the sizes of these four sets, of the two input sets, the input sets, okay, so I'll try to use that. So you take the input set to box A, okay, the input set to box B, the output set of box A, and the output set of box B. If you fix them, you fixed already some Euclidean space R to the OA, OB, IA, IB, and all correlations lives inside this space. So the correlations were just conditional probability distribution that for any two questions, for any two inputs, X and Y, you got a probability distribution over all pairs A and B of the output pairs, possible output pairs. Okay, great. So these are the correlations. This is the general definition of a correlation. And then we saw more restrictive definitions. So subsets of this set of all correlations that come from no signaling. So from cases where box A and box B cannot signal each other, cannot communicate in any way. And the first collection of correlations that we talked about were the deterministic ones. So what is a deterministic correlation? For any input, each box chooses for any input an automatic output. So for any X in IA, box A automatically chooses dA of X. So I need just a function from inputs to outputs, both for box A and box B. And the correlation is just a Dirac measure. So for any X and Y, you answer AB only if dA of X is A and dB of Y is B. Okay, so I think this is quite clear. These are the deterministic correlations. And the classical correlations, which again the name classical comes from the fact that these are the correlations that are possible if you think that the world is governed by classical mechanics. So these are just the convex hull of the deterministic ones. And we denote this set, the classical correlations, by curly C subscript C. Okay, now afterwards we talked about the quantum correlations. So what did we need for the quantum correlations? We needed two Hilbert spaces. At least for now, they are finite dimensional. So we have the complex number to some power, the complex numbers to some other power maybe. You take a unit vector, okay? So this psi is a unit vector inside their tensor product. And we should think of the unit vector as the state of the system. So you think of it as if A has a lab inside of it and B has a lab inside of it. And psi is the situation, the state in which the labs are in. Like this is the current situation. Okay, so now for any question, box A chooses an experiment and we defined an experiment using matrices, positive matrices, that sum up to the identity. Okay, so these MAX are positive matrices that sum up to the identity, and so box A has a set of experiments for any question. There is an experiment, and also box B for any question has an experiment, and we call these experiments, so for any X, the sequence of MAXs that satisfy both positiveness and that the sum is the identity, these are called POVMs. Okay, and we will talk about them more in a moment. And if we have all of this information, the correlation that we get, okay, so the probability that the boxes will answer A and B, given that they were asked X and Y, is just this inner product. So this is the tensor of the two matrices. You multiply it from the right by the column vector psi, and from the left with the row vector psi star, psi conjugate, and you get some number. This is a positive number, a non-negative number, because this is the tensor product of two non-negative matrices. And the fact that the matrices sum up to the identity implies that this is actually a conditional probability distribution. So you can check this out, that actually this function, this PABXY, gives you in this case a correlation, and the set of all such correlations is denoted by CQ and called the quantum correlations. Okay, so we talked about that last time. If you have any questions, please stop me. Great, so we said that Bell proved in 1964 that the set of classical correlations and the set of quantum correlations are not the same. Okay, and we showed the game that actually separates them, and now I'll remind you what a game is, but call it the CHSH game. The CHSH game. And actually, Tsirelson used the same game to show that the set of quantum correlations is not the set of all correlations. And actually, he proved something stronger. I will come back to it when we talk about Tsirelson's problem. But this idea that there is some functional, we have here convex sets, and there is some functional that separates them. To generate such functionals, we said it last time, we use games. So what are games? A game is a tuple of with six inputs. Okay, so we have 4 finite sets. These are the same 4 finite sets from before. A probability distribution over pairs of questions, over pairs of inputs, and some verification function, decision function, winning predicate. These are the names of V, that for any quadruple of inputs and outputs tells us whether this is a winning condition or a losing condition. So 0 means this is a losing condition, and 1 means this is a winning condition. Great. So this is just a game, and we think of it as if there is some referee. He flips some coins, and according to the results of the coins, he sends some questions, X to box A and Y to box B, out of the input and input sets for both boxes. They do their magic. They use some model of physics and correlate in some way, and they answer accordingly with answers A and B. And then the referee decides whether they win or lose according to this function V. Okay, so the referee doesn't have any shikul da'at. How do you say it in English?
Choice?
Yeah, okay, so it doesn't have any choice. He doesn't have any choice of himself. He just follows the rules of the game, and the rules of the game are this function V. Okay, so what is a game value? So I saw that there were questions about this point before. Notice that a value of a game depends on 2 inputs. You need to have a game and a correlation. Okay, so the value of the game is just the probability of winning this game if you use this correlation. This is just what val GP means. but you need to have both the game G and a correlation that is taken from the correct correlation sets, right? From R to the OA, OB, IA, IB. And this is just the mathematical formula that you need to take, but clearly this is the probability that the referee will ask questions and X and Y. This is the probability that the boxes will answer A and B accordingly. And this is just 1 when they win and 0 when they lose. Great. So let's move along. Now we can talk about Tsirelson's problem. So to actually say what Tsirelson's problem is, I need to generate more models of quantum mechanics. Okay, so we need to talk about other correlation sets that come from other models of quantum mechanics. And to achieve that goal, I need to, in some sense, talk about preliminaries. Not in some sense. I need to give you some preliminaries on functional analysis. These are very basic things. Okay. So if you're not familiar with them, this is okay. I will explain everything, but really this is basic. This is basic stuff. So a separable complex Hilbert space. So for now on, I will not say separable and complex. Just all our Hilbert spaces will be such. Is just isomorphic to either the complex numbers to some power, to some finite power with the usual inner product. Okay, so I wrote down here. If you have X, this is a vector, so it is X1 up to XD. This is X, and this is Y1 up to YD. And the inner product is just this number. Okay, this is a complex number, and this is actually an inner product. And the other example is just the set of all infinite sequences of complex numbers with this inner product, but you need to restrict yourself a bit. You can't actually take all sequences. You need to take sequences such that their product with themselves is bounded. So if you take the product of any sequence with itself, it is a series of positive numbers, of non-negative numbers. This series either converge or diverges, and if it converges, this sequence is part of this L2. Okay, I move along. What is the tensor product of two Hilbert spaces? So let's go through that really quick. If we have two Hilbert spaces, so first of all, we need to define their algebraic tensor product. You take just formal sums of pairs of elements from one from H1 and the other from H2. Okay, so the set of all formal sums of this form. But I define some equivalence between these formal sums. So there are two rules to this equivalence. Actually, you just can say that this is a bilinear multiplication, but let's say these rules one by one. The first rule is that there is the distributive law, which says that x plus x prime times y is just x times y plus x prime times y, and also from the right. And that scalar multiplication can get outside any one of these vectors and inside to any one of the coordinates of this pair. Okay, so we talked about it a bit last time, that if you take two finite dimensional spaces, their tensor product is just the span of a basis element from the left and a basis element from the right. And I defined it using what's called the Kronecker tensor product. But as it is, C to the D1 tensor C to the D2 is just isomorphic to C to the D1 times D2. Now, to have a Hilbert space, we need some inner product and some topological properties of this space after we have inner product. So you can naively just add this definition of an inner product. If you have a pair X tensor Y and the pair X prime tensor Y prime, you would define the inner product to be X times X prime from H1. So this Hilbert space has an inner product, and this Hilbert has an inner product, and you just multiply the solutions. The problem is that the elements of H1, H2 are not these kinds of elements, right? They are sums of these kinds of elements, but you just extend it linearly. and everything works out. So after you just say that this inner product is linear, bilinear, not linear, you automatically get.
Never mind. It's Q linear,
right.
but
Yeah. You are right with the conjugate on the left, on the right side. Thanks. I should have. You're right. I should have wrote probably alpha.
Yeah, it doesn't matter. Here. We all understand what's going on.
Yeah, cool. Hopefully everyone knows that. I'll go real quick, but now the point is that maybe you still don't have a Hilbert space because there is some topology now and you need everything to be complete. If you have a Hilbert space, you need it to be complete. So you complete it in the same way you complete the rational numbers to the real numbers. You complete somehow this vector space to a potentially larger vector space that still has an inner product, and this one is actually the tensor product of the Hilbert spaces. And from now on, all our tensor products are just these completions. So in the finite dimensional case, you don't care. In the infinite dimensional case, you do care. But these are our tensor products. Okay. Quickly, last time we talked about what is a positive matrix, and I just defined it using the fact that they were Hermitian and had non-negative eigenvalues. Now I'll give the better definition, okay, that also is easier to work with when you talk about POVMs and so on. So if we have a Hilbert space, there is the set of all bounded operators on this Hilbert space. So it's all linear transformations from the Hilbert space to itself, such that their operator norm, and this is the definition of the operator norm, okay, is bounded away from infinity. Okay, so the image of the unit sphere is bounded in the norm that comes from the inner product of the Hilbert space. Okay, great. So such a function, such a linear transformation is called positive, and a positive operator if for any vector from the Hilbert space, if you take the inner product of the image of the vector with the vector itself, it is a non-negative number. Okay, so it's a real number and it's not non-negative. Great, so we have the definition of a positive operator. Now, just a fact, this is true for complex, at least for complex Hilbert spaces, and these are the only examples that we talked about till now. Note that the adjoint of any such operator is itself. So it's a self-adjoint operator. And again, if you don't know what self-adjoint operator means, just think of the conjugate transpose of matrices. So this is the correct thing to think about. And lastly, let's talk about projectors. So an element inside the bounded operators of a space is called the projector, or an orthogonal projection, if it is both an idempotent, okay, so the p squared is equal to p, and it is self-conjugate. And last time, Guy talked about the fact that you can think, instead of thinking of POVMs, on these positive matrices, on experiments as positive matrices, you can think of them as just choosing a basis. He talked about it that way. And the point is that the way to explain, to model correctly what Guy said last time, is that instead of using positive operators, you actually use projectors. And the projectors are just, as they sound like, project on a subspace all vectors, and then they can be defined only using some basis, right? To any subspace that you project on, you can take a basis, and together they are all an orthonormal basis, and you get all the information that you need. Great. So as I mentioned right now, last time we talked about experiments, and I said that these experiments or measurements are defined using these POVMs. And now we have the more general definition of a Hilbert space. So let's define what the POVM is on a Hilbert space. So a positive operator valued measure is a sequence of positive operators, not operators, such that they sum up to the identity of the Hilbert space. Okay, so this is just a POVM, and like we said, this is modeling the concept of doing an experiment or measuring something about our system. If these are all projectors, so if all these MIs are projectors, This is called the projection valued measure. So this is a PVM. So when I say PVMs, I mean that all these operators are projectors. This is the case where this is what Guy talked about last time. Great. Now we can define other models that interest us. So now we can define other correlation sets. And this interlude was dedicated for us to have them to tackle the more general definition. But the more general definition looks the same as the specific definition in the finite dimensional case. You just replace every finite dimensional vector space with a potentially infinite dimensional Hilbert space. So if you have two Hilbert spaces, HA and HB, for any input Alice can have, okay, so box A, I call it now Alice, the box chooses beforehand some experiment, but now an experiment is just a POVM in the more general definition. So these are positive operators, all the MAX that sum up to the identity. Also, Bob, again, for any question, has some experiment. So he defines a POVM for any question. They share some unit vector, psi, in HA tensor HB, okay? And again, we should think of this psi as the current condition in which our system is in, so the current state of the system. And the correlation that is obtained is the following. So I wrote both the thing I wrote last time. So you can think of it, this is the functional, the conjugate of psi, and you apply it on the image of psi under the operator MAX tensor NBY, but maybe an easier way to see that is that you take the inner product of the image of MAX tensor NBY with psi, comma with psi, okay? So this is this number, and since these were, okay, so we had the definition of a positive operator, you see that TV, comma V is greater or equal to 0. So if you remember that, you see that this number is at least non-negative. And again, you can check that the fact that these are POVMs, okay, so the fact that the sum over A and B, so A from IA and B from IB, over all these MAX tensor NBY, okay, you can just check this is the identity tensor and identity of HA tensor, the identity of HB. And this fact implies that the sum of all such numbers when you go over all the ABs is 1. And this implies that this is actually a probability distribution. So a conditional probability distribution for any X and Y. Okay, great. So this set of correlations, so you just changed the definition that we had before with potentially infinite dimensional Hilbert spaces, you get what's called the quantum spatial correlations. Now, the name spatial means that you think of HA as the part of space that is in box A, and HB as the part of space that lives in box B. Okay, so the name spatial comes from the fact that there is some spatial, you can define the whole space using some product, some tensor product of two parts of the space. Okay, great. And box A only acts on its part of the space, and box B only acts on its part of the space. This is very important. Great, so these are the quantum spatial correlations, and we denote the set of all such correlations as CQS. And now we can talk about quantum commuting correlations. Okay, so this is a more general definition. You can check that all previous correlations lives inside this definition. And at least the buzzword to say here is that in algebraic quantum field theory, sometimes there are calculations where you cannot tensor out the Hilbert space. You cannot separate, in some sense, the Hilbert space into two subspaces such that the whole Hilbert space is the tensor product of them. And it's just easier to think of calculations, but you still want this notion of, okay, so I'll tell you something about that. The point is that when they are spatially apart, and you use the model that we talked about before, it doesn't matter whether Alice is doing its experiment first and then Bob is doing his experiment afterwards, or the other way around. So the fact that Alice did her measurement doesn't imply anything on the measurement of Bob. Okay, so they will correlate, but they don't affect each other. So another way to model this thing is just to, instead of thinking of two separate Hilbert spaces and tensoring them, is just thinking of a single Hilbert space, but asking that all the measurements commute. Okay, so every measurement of Alice and every measurement of Bob commute with one another. And then actually the fact that Alice is measuring things before Bob or vice versa doesn't do anything to the result. So the result is not affected by the order in which they conduct their experiments. So this quantum commuting model, you should think of it as the situation where there is no easy way to make the space separate, but you can still model the fact that it doesn't matter which one goes first. Okay, great. So let's read what's written here. So now our whole space is just a single Hilbert space. We don't have a tensor product. And again, for any question that Alice can have, she has an experiment, but now the experiment is acting over all the space. And also Bob is acting over on all the space. But now, as I said a moment ago, we ask that the measurements that Alice conducts commute with the measurements that Bob conducts. So the POVMs of Alice and Bob all commute. So this is this equation, okay? Again, they need to share some state. So they need to share what is the state of the system, what is the condition in which they begin their experiments. This is the psi, the unit vector psi. And the correlation that they obtain is the same. So you just act with MAX and NBY on psi, and you multiply it with psi conjugate, or you can think of it as the inner product. And the set of all such correlations, this is, as I said a moment ago, a bigger set, is called the set of all quantum commuting correlations. Great. So we have this definition.
Wait, it's a bigger set or a smaller set? Because
okay, so you can check that the tensor product model always satisfies this thing. So you see here, there's this HA tensor HB. You call it H. And you can check that these POVMs, these MAXs, are actually MAX tensor the identity on HB. And these NBYs are exactly the identity of on HA tensor NB. Oh, just a moment. Great. Are you hearing me?
Yes.
Great. NBY. And these operators come from BH. Okay, so these are bounded operators on the tensor product, and they commute with one another. So this is a private case. How do you say it in English?
Special case.
Yeah, special case of the quantum commuting model.
But isn't the quantum commuting model a special case of the previous one?
No. This is no.
But
the quantum
also,
commuting model is more general. Potentially, there are more correlations in the quantum commuting model.
But can't you just take H1 equals HA equals HB, and I mean, you see what I mean?
But the space is HA tensor HB. This is what I said here.
Okay.
The space, the H is the tensor product of the Hilbert space of Alice and the Hilbert space of Bob.
And in the other one, you have psi in H. That's the difference.
Right, psi is in H itself, not in the tensor product of H with itself or something.
Okay. Yes.
Okay, so here you cannot, how do you say it? Decompose. Okay, you cannot decompose H into a tensor product such that all the experiments of box A act only on the left part and all the experiments of Bob of B only act on the right part. So this is a more general condition.
Michael?
Great, so yes.
There is another question from Amit Behara. asking, is there a physical meaning of the quantum commuting correlations, or is it just a way of extending quantum spatial correlations?
Okay, so I don't know what are the exact cases in which this is a good model. Okay, so as I said, the buzzword is quantum field theory, algebraic quantum field theory, but I'm not the one to elaborate any more about this point. At least for now, let's just say there are these two models and they interest people. So we ask questions about them. Okay, so let me just move along. We said that the quantum correlations are exactly the quantum spatial correlations when we take HA and HB to be finite dimensional. It turns out that if you take the quantum commuting model and restrict yourself only to finite dimensional Hilbert space, you again get the quantum correlations. So both of the previous models, if you just add the restriction H or HA tensor or HA, HB are both finite dimensional Hilbert spaces, you get this correlation set CQ that we talked about last time, and also that I reminded of you at the beginning. Now, yes.
I mean, it sounds quite surprising. Why is it true?
Okay, so you ask why when I restrict this model, when I restrict this model, I still get the same set. The point is that you can model the same experiment using a potentially larger HA and HB and in their tensor product. So you can replace this H potentially with HA tensor HB that are maybe other HA and HB, but in that case, like in this new place, this decomposition exists. We will go through it, okay? Hati?
Okay.
So we will just prove at some point that when we restrict to the finite dimensional case, we get the same thing. Okay, so now the last correlation set that I want to talk about is what's called the quantum approximated. And I just want to note that usually when we play a game, we think of, I don't know, the best way to play this game, right? So what is the best way to play a game? It's just a supremum over the set of all possible correlations that we think that we need. But a supremum is the same as taking a maximum over a closed set. So just take this CQS. I'm not saying that this CQS is not closed, but potentially it is not closed. So maybe when you take the supremum over CQS, you are actually taking the maximum over the closure of CQS, and we call this closure CQA, so the quantum approximated. And the only thing I want to say about this point is that any correlation in the quantum spatial case, so in the quantum spatial case, lives inside the closure of the quantum correlations. So it is true that any correlation that comes from the tensor model, tensor product model with infinite dimensional Hilbert spaces can be approximated using finite dimensional Hilbert spaces. So this means that if you take the closures, if CQA is the closure of CQS, it's also the closure of CQ. Okay, this is just a fact. And now I can talk about, at last, I can talk about Tsirelson's problem. Great, so we had—
Sorry, was there a notation for the Q approximation?
CQA.
CQA.
The quantum approximation.
And CQC is closed?
Ooh, that's a very good question. Who asked that? I didn't know.
Me, Itai.
Itai. Okay, it is not clear, but it is true, and we will need to. Okay, I thought at the beginning that it is not that hard. It is not that hard, but when we will talk about the connection between—
Sorry, Mikhail, I must have missed what? I'm sorry, what are we talking about now?
Itai asked whether this set is closed. in the topology, in the Euclidean topology. And I said that the answer is that, yes, this is closed. But it's not that clear. Okay, so showing that any sequence of correlations that come from this model has a limit is not that easy. That, yeah, that converges, the convergence is to a point in this set. This is the point. Yeah. Okay, great. So I'll just go through quickly on what is written here. So this is the set of all correlations. This is the set of quantum commuting. So this is the case where there's a single Hilbert space. This is the quantum approximated. So this is the closure of that, which is the quantum spatial. Okay, so QS, this is quantum spatial. I will not write that down. This is the quantum. So this is the case that we talked about last time. And this is the classical. So as we said last time, Bell already showed that this set and this set are not the same. So there is a strict inclusion between the classical correlations and the quantum correlations. Great, this is a result from 64. And what actually Tsirelson proved is that even if you use the quantum commuting model, so last time we said that the CHSH game had the following property: the supremum over all val CHSH together with P, where this P is taken from the classical correlations, this thing is smaller or equal to, okay, it's not smaller or equal, it's just equal. My eraser is too large. It's just is equal to 0.75. Okay, so the maximal winning probability using classical correlations is 75%. But if you take the same supremum and you replace it, you just take the quantum correlations, this is exactly 1/2 times 1/2 plus 1 over square root of 2, which is strictly larger. So this is the way, and the fact that this is an equality, so we said that this is larger or equal to this number, and the fact that it is also smaller or equal to this number is a result by Tsirelson. But actually what Tsirelson proved is that even if you take this, okay, so let me even take this thing again. Okay.
Michael, you mean 1 plus 1 over root 2? Michael?
Exactly.
Why 1? Maybe I need 1.
It should be more
Otherwise it's too
than
small.
3/4, right?
Yeah, maybe this is, yeah, right. 1 plus 1 over square root of 2, 1/2 plus 1 over 2 square root of 2. Okay, great. This is about 85%, about 0.85. Great, but the main point is that Tsirelson proved a stronger thing. He proved that actually if you even take the quantum commuting model, you are still bounded from this number. So this is exactly the same number. Even if you enlarge the set, this is again 1/2 times 1 plus 1 over square root of 2. Okay, so what actually Tsirelson proved is that this inclusion is strict. So Bell showed that this inclusion is strict. Tsirelson proved that this inclusion is strict. Tsirelson also showed that at least in the finite dimensional case, this model, these 3 models are the same. So this thing, and this thing, and this thing. So these 4 models are the same in the finite dimensional case. This is what Nati asked about. And you can say that now you have 3 Tsirelson problems, okay? You can ask yourself whether this is a strict inequality or a strict equality or an equality, whether this is an equality and whether this is an equality. But there was a reason why I showed you, I marked with red this inclusion, the inclusion here. There are two reasons. All the inclusions here are quite easy to prove, except this inclusion, okay? So the fact that the closure of the quantum spatial correlations sits inside the quantum commuting is not easy. It's not that easy, and it follows from the fact that it is closed, right? If you show me that it is closed, this is clear, but I said that it's not so easy to show that it is closed. And the other reason that I marked it with red is that this is called the Tsirelson's big problem. And this is the Tsirelson's problem that we talked about last time. So when we say Tsirelson's problem, we actually mean whether this inclusion is strict or is it an equality, okay? So after the break, I will explain at least why, if we have an equality between CQA and CQC, it automatically implies that MIP star lives inside R. So any problem inside MIP star is decidable. You can decide for any problem in. Okay, so any decision problem that is inside MIP star can be resolved, can be computed whether this is a yes instance or a no instance in a finite amount of time. Great, so let's take a break. We come back at 5 o'clock. And
I have a question.
Yeah, okay, but I think I'll. You can ask questions throughout the break, but I think we'll let everyone that wants to just take their break.
Yeah, Michael. So
yeah,
you mentioned a relation between CQA and the closure of CQC. Could you repeat that? No, something like that.
No, I said that, okay, what do we know? It is very clear that this thing is included here. We said that the quantum commuting model is a more general model than the quantum spatial one.
Right.
But why does it mean that the closure of, maybe the closure of CQS is larger than CQC, right? So there are sets who are included in other sets, but their closure is potentially larger, or maybe they are just not comparable. Maybe no one is living in no one else. So the fact, how can you deduce that this inclusion is true if you show me that
CQC is closed?
Yeah, exactly. If CQC is closed, if you are included there, also your closure is included there.
Right.
So I'm just saying that the red inclusion is a consequence of the fact that CQC is closed, and we will show it. We will prove it at some point.
Okay, thank you.
You're welcome.
Michael, you said that CQ and CQS of the same closure. Why is that?
Okay, it's not that clear, but I'm claiming that any correlation that comes from CQS can be approximated using correlations that come from the finite dimensional case.
Okay, I think I can.
Okay, at least, you know, like intuitively, you can chop up, like you can say something like, okay, most of the positive operator that I'm using now has some, how is it called, a corner, a large enough corner that contains most of its weight, right? Something like that. And then you get some finite dimensional thing, and then you can, I don't know, take something that is close to this thing and hope that it gives you a correlation that is close. And this kind of argument works.
Okay, I think I can imagine that.
Yeah, you can think of the bounded operators on this infinite Hilbert space as just infinite matrices, right? And you just chop out the finite part of them and hope for the best. And you can do it in some smart way that actually approximates this thing, okay?
Can I also take you back a bit to the classical correlations?
Yeah.
You said that the classical correlations are the convex of the
convex hull of the deterministic ones.
So yes, I don't quite see it. I think there's some background that's missing here because so why is that really?
This is the definition. I'm defining the classical correlations as the convex hull of these deterministic ones.
Okay.
You can define it this way, but it's just true that every distribution is in the is a convex combination of deterministic unique choices, right? So,
but it depends on what do you mean by distribution. Like you need some rules, and you can say that the rules are just taking the convex hull. You are correct that you can give other rules.
The classical correlations you get. What are the classical correlations? It's just the set, or a classical correlation is one distribution for each pair of questions, for each X and Y. Right?
I don't understand.
You choose,
say it.
For every X and Y, pick a distribution over A's and B's. Once you do
no, this is too large. I don't understand. This is too large of a thing. For any X, A needs to decide. No, okay. Well, we need to think about it for a moment.
These are the classical correlation.
No, this is too large. What you just said is all correlations.
Okay, no, sorry. Yeah, but still, wait.
Okay. Anyway, there is a definition of classical correlations that is not so straightforward. You add probability and so on. Like they have some. Okay, so they can roll some dice beforehand and so on.
Where I was wrong is that you choose a correlation for every X.
Yeah, right.
For every Y. You don't do it in the same.
Yeah, I think that's what I was thinking. It is also like.
So it's like independent randomized strategies for the Alice and Bob, right?
Yeah,
which are independent of each other.
But they can share randomness beforehand, so they can share random bits beforehand, and they can also use other random bits that they generate themselves afterwards. But it's the same. You just get the convex hull of the deterministic ones.
Okay.
But I don't think it's a triviality. I think it's a little bit like Birkhoff's theorem that doubly stochastic matrices are the convex hull of permutations. So it's a similar kind of result.
I see.
So we have this question.
No, wait, Andreas. If you say that in the finite case. Okay, I need to think about it.
It's not the same result, but it's a kind of this type of result. Yeah. That.
Okay, I need to think of that point, but I thought it's quite clear. But maybe there is something here. Okay. Other questions? Someone.
So the question on the chat, I don't know if it was discussed. I didn't pay attention to what was discussed, but do we really know that CQ is strictly included in CQS?
That's a great question, but I don't want to spoil the answers. So all of these inclusions are known whether they are equalities or inequalities. So this is all Tsirelson's problem are now like it is all known now. I will say it after the break, okay?
Michael?
Yes.
How did we define the C without subscript?
I don't hear you so well. Who's talking?
Without subscript, how did you define it?
The set of all correlations. These are just the all conditional probability distributions.
Okay.
But isn't the Tsirelson results from 80 automatic, because there is some kind of independence that quantum correlations have? There are some formulas that show
maybe saying it like this is a triviality, but saying it like this is not a triviality.
Agree.
Yeah, so as I said it, maybe it's very clear, but But actually what he proved is that you should think of Tsirelson's result as saying something like the CHSH game does not distinguish between any of these models, which is maybe not a triviality. And also claiming that you can, okay, this is some algebraic trick. Tsirelson's proof is very easy. It's not a hard thing to show, but this is a nice algebraic trick and we will show it. So anyway.
Yeah, thanks.
There is this method of taking a PVM, a projective valued measure, and generating from it a unitary. And this is what Tsirelson used, and this is a very basic tool in all these proofs, and we will see it throughout the seminar. This translating a projective valued measure into a specific unitary, and this unitary is called an observable. And anyway, this kind of argument will follow us throughout the seminar.
Thanks.
By the way, Michael, if someone, I don't know, is Dorit still there? For example, Dorit or Miki Benor, I don't know, can say a few words about how this, how this connects to physics.
Yeah, so
I would be delighted to find out.
Nati, I'll just say that at the end, I will ask people to maybe give some talks, and I wrote there like some introduction to maybe the more physics part of it.
Yeah, well,
you can elaborate now. But...
What, Dorit?
I can say one thing that basically in quantum gravity, for example, there are lots of situations in which a tensor product structure is not something that is given to you. It's like tensor product structure is how physicists think of, like in first, I don't know, quantum class, you learn that different particles are assigned different Hilbert spaces, and to put particles together, you take the tensor product. But this is not the way things happen in quantum gravity, for example, and in many other situations. But still, you want to describe a situation in which you have different systems, and you want to say what a different system is. And the only way to do it is basically to say operators here commute with operators there. So that's the origin for the difference between the two different things. But as we know, they're the same in finite systems.
So why are the infinite systems at all interesting for physicists, or are they not?
You'll have to ask a physicist you'll have to ask Eliezer Rabinovich, for example. I mean, in quantum gravity, you talk about infinite energies, and I think things don't really make sense when you put a cutoff. It's like an artificial cutoff if you make it finite.
Yeah, I think like, okay, I know what I'm saying may be total bullshit, but there is something called a condensate, which is very basic in quantum field theory. And the condensate is somehow inherently infinitely, it inherently has infinite dimensions. It's a place where you have absolutely no idea what the energy level of some particle is, or something like that. So it can be anything between 0 and infinity, or minus infinity and infinity, something like that.
I think there are examples that are much more basic. I mean, for example, if you take only a single particle in one dimension, then the Hilbert space will be L2 of R.
Yeah.
I was talking about a more sophisticated example in which you actually don't know what that you're likely to be in lower energies, and that it's possible to take a cutoff in a reasonable way. I think, Guy, right?
Yeah, somehow L2 of R. I'm really, don't trust anything that I'm saying, but L2 of R I think some people think of it as just an approximation, and that actually the universe might not be continuous, but I guess still it's an infinite dimension, but it's, yeah, I don't know. Forget what I said. Yeah, maybe L2 is good enough example.
Okay. If you, I think this discussion is very important, and if I'll talk at the end if anyone wants to maybe construct a rigorous introduction into like why these models are interesting and where, like I threw some buzzwords, and I just want to take these models as given, but the motivation is very interesting. So let's do this discussion in a more deep way and later on. Okay, so I'll resume the talk. So last time we said that the fact that MIP star, so I didn't remind you what MIP star is today, but that's okay. I'll just say what the implications were. So if MIP star is equal to RE, it implies actually that CQA, CQA is not CQC. Okay, and I'll explain at least why this is true. Okay, so last time.
Wait, about the other containment, are they known by now?
Yeah, all of them are known. So this is from. I'll say who proved each one of them. So just a moment. It will take me a moment to erase all the mess that I've done here. Okay, so this is the new result. So this is G, Natarajan, Vidic, Wright, UN. Okay, 2020. This one is Slofstra from 2017, I think, 16, 17, something like that. This is Colodangelo and Stark, Coladangelo.
When you say this, you mean the strict inequalities?
Yeah, all of them are strict inequalities. So this is a strict
when you say this, so like
this,
the non-strict is much easier.
Okay, what's not, everything here is a strict inequality. So it turns out everything here is a strict inequality.
Just showing that there is a non-strict
inclusion.
That's more or less trivial.
The weak inclusion is
the weak inclusion. Yes, I forgot the word. Yes.
Yeah. All the weak inclusions except the red one are trivial. The red one is not that hard, and the fact that they are all strict is okay. So this one is not that hard. Okay, this one is very hard, and this one is extremely hard. Okay, and they were all solved in the last 3 years, so this is quite nice. Actually, the fact that this thing and this thing are not the same is a previous work of Slofstra, and you can say that this was actually Tsirelson's original problem. So, like Tsirelson asked just whether the quantum commuting and the quantum spatial models are different. So already Slofstra showed that the quantum spatial and the quantum commuting models are different. But the fact that you cannot approximate every quantum commuting correlation using quantum spatial correlations, which is the new result, this is a strong refutation of Tsirelson's problem. Like you should think of it that you actually can separate them, not only the fact that there is an accumulation point that is outside of CQS. There are points that are far away from CQS that lives inside CQC.
I have a question. This theorem at the bottom of the slide, does it imply that if the provers are restricted to only have a finite dimensional common vector, then all they can prove is in R?
No, this is not true. No. We said last time, think about it. We said last time that already approximating the quantum value of a game. So let's recall something. This number that I wrote here in this bracket, okay, so the supremum over all these things, we called it last time val q of g. Okay, so it's the supremum over all quantum, over the value of the game using all quantum correlations. Great, and we said that approximating this number in the finite dimensional case is in RE. So distinguishing between the case where this value is larger than 2/3 or smaller than 1/3 is okay. So
sorry, is in RE
if you
or
could have solved it, okay,
is
just one.
complete. Sorry, Michael, is in RE or is complete for RE?
I didn't hear what you said.
Is in RE or is complete for RE?
Okay, the fact that it is in RE is not that hard, and I will talk about it in a moment again. I mentioned it for a brief moment at the end last time. I will say some more at this point because this is a good point to remind you that. But the other way around, the fact that this question is complete for RE, meaning that it reduces, you can reduce the halting problem to this problem. This is the work here. Like this is what Gina, Tarajan, Vidik, write you and proved.
Okay.
Okay, so okay, let me explain what is the theorem downstairs, because this is not the actual theorem. This is in some sense a corollary of the theorem. So the actual theorem is the following one. We had the classical value, which was the supremum. Okay, so given a game, you can calculate its classical value, which is the supremum over all classical correlations. You can calculate the quantum value, which is the supremum over quantum correlations, but is also the supremum over quantum spatial correlations, and it's also the supremum over quantum approximated. So val q of g is the same as val qs, which is the same as val qa, because we said that the supremum is just over the closure. So the fact that CQA is the closure of CQ and CQS automatically means that this value is the same. This supremum is the same. So I'm erasing the val QS and val QA, so since they are the same. But you can ask whether potentially there's this commuting, quantum commuting value of the game. So at least it's not clear that the supremum over all quantum commuting correlations is the same as the value of the commuting ones. And it turns out that there is an algorithm. There is an algorithm that approximates this value from below. And I mentioned how you should think of this thing.
Sorry.
We saw that.
What is this? Sorry, Michael. This. This.
I wrote it here because I meant the thing about it.
Okay.
Okay. So how do you generate this algorithm? For any dimension, you think only on the case where HA is isomorphic to HB, is isomorphic to some C to the D. So now the fact that there
again,
are many...
what is the input? What is the input of the algorithm? Can you remind?
Okay, the input to the algorithm is a game, and you want to approximate from below the
so the input is the measure and what else?
The function V.
Okay, the four sets, the measure function, and the verification function. So the predicate, the winning predicate. Okay, so I give you a game in some finite format, and you need to decide what the quantum value of it is. Okay, so I'm claiming that you can approximate it from below. You can generate a sequence of non-negative numbers that is, okay, so you will generate something that we will call alpha 2, and then you will generate something called alpha 3, and then you will generate something called alpha 4, and so on and so forth. And this sequence of numbers will converge to this value. So the limit of this thing is val q of g. And now I'm explaining how should you do it. So it is independent of the game, except that you need to know what are the sizes of OA, OB, IA, and IB. Okay, so how do you do it? You just say that, okay, it is true that CQ is a very complicated set. But if I restrict you to only use the part of CQ that comes from two-dimensional strategies, okay, so you are now allowed only to use like HA is C to the 2, C squared, and HB is C squared, and now you need to choose matrices, 2 by 2 matrices on the left part, and 2 by 2 matrices on the right part, and these are the measurements and so on. This is not such a complicated thing, and you can approximate it using some epsilon net. Okay, so for any epsilon, you can find a sequence, a finite set of correlations that is epsilon dense in a finite set of correlations that is epsilon dense in those correlations in CQ that come from the two-dimensional situation. Okay. Now just check all of them. Take all these correlations, put them in calculate the value for them. You get some sequence of a finite sequence of numbers. Take the maximum out of them. This is alpha 2. Do the same thing for the three-dimensional case, and now make epsilon a bit smaller. The maximum over this finite set will be alpha 3. Now you can prove that at some point, if there is a very good quantum, the fact that you can approximate that val q of g is some supremum means that there is some dimension where you can approximate this number up to any constant that you want, right? And the fact that you took the maximum here and the fact that you took an epsilon net means that one of the strategies that you check along the way is very close to the good strategy, to the best, like to an almost perfect strategy, which means that you will get an almost perfect value because everything here is continuous.
But don't you also have to compute the epsilon net?
Yeah, but this is easy. That's easy. Everything here is
okay.
Yeah, the fact that you can take projective measurements should imply that you only need to take some dense sequence of bases, right? Like epsilon dense sequence of bases, and this is easy. Okay. So for example, for the two-dimensional case, you should think of it like taking this basis and then taking this basis and taking this basis and so on. And you just move at each step small, right, in a small angle or something like that. In this case, you can cover all the cases, the two-dimensional cases. Okay, so this is an algorithm that approximates this value from below. What does it mean? This automatically means that if any of these numbers, so you do this calculation, if at one point you are greater than 1/3, you know that the value of this game is greater or equal to 2/3, right? Because we stated that the games that we are given are either larger or equal to 2/3 or smaller or equal to 1/3. This proves that MIP star is in RE. So this means that if the algorithm halts, you can show that it halts. It will just halt at some point and you will say, yes, this is a yes instant. But if it doesn't halt, so if it never crosses 1/3, we will never know it. So the sequence can go further and further on, and we don't know at any specific point whether at some point it will be greater or equal to 1/3, or we need to wait, or we will wait and it will never happen. So this is exactly like you should feel like it's the same as in the halting problem. But quite amazingly, this number can be approximated from above. So what?
Wait, Michael, it's a little
these-
strange. It's a little strange what you just said. It's a
What?
big difference. It's a big difference with the halting problem. I mean, I
Okay,
find it a
maybe
little hard-
explain.
No, I find it a little hard to believe that you cannot get an estimate on which dimension. So if you have to make the jump from 1/3 to 2/3, can't you get any estimate in which dimension it will happen?
Okay, so Nati, this is a very good question. One of the results from this paper is that you can construct games with value 1, so 100% probability of winning,
right?
But you can take the dimension needed for, to win value 1 to be as large as you want. And for any smaller dimension, you will win with probability at most 1/2. Okay, so to win with probability more than 1/2, they can create games that, for, I don't know, Google.
Googleplex. No, I understand.
Yeah,
but
dimension,
still,
you are only value 1/2. So for any
no, I understand.
strategy from that.
I understand, but can't you get an estimate for this Googleplex?
Okay, this is exactly what this result says. You cannot. You
Yes.
strictly cannot estimate the correct dimension in which you believe there should be a good strategy. If you could, this is just an easy search, right, Nati?
Right. No, I understand.
So in some sense, this is the essence of the problem. You don't know what is the size of the dimension needed to solve your game. Maybe it's you just didn't go large enough.
Okay.
Great. Okay, so I'll come back to the quantum commuting.
Let me just say it maybe in a more concise way. So a corollary of this theorem, of the previous theorem of that MIP star is RE, a corollary of that is that given a game and a number, deciding if you can approximate the value of the game with a space of the given dimension, that's RE complete. That's complete in RE.
Okay, I need to think about the way you said it right now.
Because if you could know the number where you already, the dimension in which you already get a good approximation, you would find that number, and then you would just enumerate.
Yeah, you have no way of finding this number or even having any bound on this number. You can generate games that can be played perfectly, but a priori you will not know where is it heading? Like where are you getting closer to 1 using the dimension?
But this number exists, so you know you can go on till you'll find it.
If I'm telling you that this is a value 1.
No, I need between 1/3 and 2/3. So I know there's so I just go till I find an approximation, which is epsilon, which is.
But you don't know when will it be.
I'll continue till I'll find one.
But maybe there is no one. This
So
is
the
why the
point
no
is-
instances. This is why the no instances are not computable, because you
Exactly.
never know when to stop.
So it's a recursive sequence of games, but the dimension that you need to go is an uncomputable function. So it grows too fast.
I don't want to jump to the way they prove MIP star is equal to RE, because I think we will talk about it next week. I will talk about like the exact methods. But the only thing I wanted to say here is that a yes instance, if you I'm telling you that you have a game, it's either val q larger than 2/3 or val q smaller than 1/3. If I tell you that I gave you a game and it's either the value is either greater or equal to 2/3 or smaller or equal to 1/3, there is an algorithm that at least in the first case will stop and say, aha, this is true. It's greater or equal to 2/3. How do you do it? You do this, you calculate this sequence
Go by
And
dimension.
if it is greater or equal to 2/3, at some point you will see it because it will be strictly greater than 1/3. The point is that if you are in the second case, you will not know that with this algorithm. This algorithm will not tell you that you are in the second case. So this sequence can be computed forever, and you will not know.
Yeah,
Okay.
This is the whole thing. Yeah.
So this just shows that this problem is in RE, not the
Yeah, this just shows that it is in RE. I just mentioned that these algorithms, the result, the consequence of this MIP star is at least contained in RE. This is an upper bound on the complexity class MIP star. Great. The other way around, okay, so val QC, this is the theorem that says that this thing can be approximated from above. So the quantum commuting value can be approximated from above. Meaning, what they showed is that you can generate a sequence of non-negative numbers, beta 1, beta 2, beta 3, and so on, that converges, it's non-ascending, it can only decrease, and it converges from above to this value, to the quantum commuting value. Okay? Note that if Tsirelson's big problem is inequality, Tsirelson's problem is an equality. In particular, these numbers are the same. So you can approximate the quantum value from below using this algorithm, and you can approximate the quantum value from above using this algorithm because these numbers are the same. This means that MIP star, if you can approximate the quantum value both from below and from above, you can distinguish both between the greater or equal to 2/3 and distinguish the smaller or equal to 1/3. This means that this is a decidable problem, that any problem in MIP star is decidable because you can actually approximate the quantum value. And when you approximate it, you will converge to the correct value. You calculate alpha 2, and then beta 2, and then alpha 3 and beta 3, and then alpha 4 and beta 4. And at some point, if these values were the same, at some point, the distance between the alpha i's and beta i's will be as small as you want. And this means that you can actually stop at some point and say, yes, this is the greater or equal to 2/3, or no, this is the smaller or equal to 1/3. This is an important point. Maybe this is a good time to ask questions and discuss.
So I have a question. Do we know what's the complexity of val QC? Is it also RE?
This is an open problem. What I just said that this is in RE core, right? Core RE, I should have wrote it like this, right? The complement of RE, because every no instance is decidable, but this is not known to be an equality, at least now.
Wait, what is not known to be an equality?
Okay, so there is the Q gap problem, deciding whether val Q is greater or equal to 2/3 or val Q is smaller or equal to 1/3. You can ask the same about val QC. If I'm giving you a game and either val QC is greater or equal to 2/3 or val QC is smaller or equal to 1/3, decide.
You don't know if this is core complete or.
Yeah, exactly. It is known to be in core, but you don't know that it is core complete. Okay, so we dived back again into the complexity part, but I just wanted to say that this is the connection between Tsirelson's problem and MIP star is equal to RE. So it's very clear that if you have this theorem and you know the algorithm that we talked about, it means that Tsirelson's problem implies that you can approximate the quantum value. But since the Q-gap problem is RE complete, you cannot approximate the quantum value, which means that Tsirelson's problem cannot be an equality. It must be a strict inequality. So we saw that this is strict inequality. Great. Okay, so
just to clarify, when you talked about the algorithm of the val HUJI, the lower bound approximation, I think you were basically referring to the fact that you're going over all projective measurements, not over all PCMs in one dimension, and then you use the dilation theorem.
Right, I use Neimark's dilation theorem.
Right, so I don't know if that wasn't a bit confusing.
Maybe.
Yeah, I also asked myself, why did you only look at projectors?
Okay, so there is some theorem that when we will talk, we'll give some introduction to quantum information theory. This is a very basic result called Neimark's dilation theorem that says that any POVM can be simulated using a PVM. Okay, so any correlation that comes from a POVM can be simulated using a projective valued measure on a potentially larger Hilbert space. But if the first Hilbert space was finite dimensional, the new Hilbert space is also finite dimensional. So you can actually use only PVMs, okay? Only projective valued measures. This is not a triviality. There's something to show here there. Okay. It's a good time to keep on the discussion if you want, but
so there are some questions in the chat. You might want to.
I don't read the chat, so
yes.
if someone can just
there
ask
are two
me a good question.
questions. One of them I'm not exactly sure of the formulation. It asks, do we know that MIP core is not in R? Do you understand?
MIP core. This is MIP core, distinguishing between val Q of C greater or equal to 2/3 or smaller or equal to 1/3. This is what's called MIP commuting. Okay, so the MIP that comes from the commuting model, the quantum commuting model, and it is known to be in co-RE. This is what I just said. It is not known whether this is a co-RE complete problem, as I mentioned a moment ago.
But it's asked whether it is in R.
If it was in R, it would also be. It would, if it is in RE, it's both in RE and in co-RE, which means that it is in R. Okay, but this is also not known. Like, we don't know the strength of MIP core. We don't know whether the quantum commuting value, distinguishing between the 2/3 and 1/3, we don't know what the strength of this complexity class is.
Okay.
There is an upper bound, co-RE. We don't know about a lower bound that is at least at this point. Okay. Other questions in the chat that I should answer before we move on to Cohn's embedding problem? We will just start talking about Cohn's embedding problem because it's important.
I think the question is not about a lower bound for MIP core. Sorry.
Yeah, so an upper bound is co-RE. This is what I said now. It's not known whether this is also a lower bound.
But there must be some lower bound known.
No, I asked the question, and it seems to me like it should be easy to prove that it is not included in R, just R.
Maybe. I'm not sure. Maybe it's possible, but I really don't know.
Okay. Thanks.
Maybe if it was okay. Maybe no, I'm not sure. Why is it that to show that it's not in R?
I thought that it is easy. I mean, R is a small class, no?
Oh, forget R. Is it easy to show that it is not in P?
I don't think that's known.
You say that even that is not known. Interesting. Okay, so actually approximating this number is wide open. So approximating this is is equal to RE, but approximating this sounds very open.
Does this open question have also important consequences like the first question of val Q? Or like did the authors say something?
Okay, I'm not the expert. Maybe
okay.
Maybe at some point we will give them more. We will ask either of the authors of this paper to come and talk with us, and they will probably have good points and good follow-up questions. I must say that my motivation is groups. So my motivation is asking whether this proof can be altered in some sense to give non-hyperlinear groups. And I believe there is a large portion of the audience that is also interested in this point. And at least to this open problem, I will give very lots of attention, okay? Whether you can—
So non-hyperlinear implies not sophic?
Yes, this is true.